All right, so this is lecture 8 of Math 331 problem solving. And so what we're going to do today is we're going to finish up our unit on recurrence relations. There's a really nice article online on the distribution of the longest run of heads. So if you toss either a fair coin or a biased coin and you want to know what's the sequence of longest run of heads, this is a very interesting question, especially if you go to Vegas. It turns out you can set up some really interesting recurrence relations, fascinating behavior as to what happens. Unlike almost every other process I know, the variance is bounded as n gets larger and larger. So you have what's called tight concentration. So the longest run of heads grows, which is not surprising. You know, the more coins I toss, the longer I expect my average run to be. And it grows on the order of log n. But the variance is bounded by 4. So the fluctuations, it's phenomenal. It becomes extremely tight. And in fact, a double exponential is involved in this. And you know, anytime you see a double exponential, that's not a cookbook problem. That's worth seeing. All right. So Catalan in generating functions. So again, the problem was we have some grid. We start here. We end here. We never want to come above. So we look at all the paths in here. And the conjecture is that Cn is 1 over n plus 1, 2n choose n. And we had the following beautiful recurrence relation. Cn was the sum, I think k goes from 1 to n, of ck minus 1, Cn minus k. And the question is, how do we solve something like this? Given that this is not something of the form r to the n, if we just tried our divine inspiration would fail. If we try this as a divine inspiration, this is now a, Lord help us, messy algebra problem. Could we prove this by brute force? So I'll leave that as an exercise. But I will not assign this as an exercise. When I was in college, I took a graduate mathematical physics class, and there was only one homework problem I refused to do. It was just such a long, painful brute force computation. I could see how to do it. I could see the number of pages required. It was just not worth the one homework problem. This one may not be that bad. I haven't tried it, but if you know the answer, is that enough to figure it out? Could you actually go through and do this? The idea is a generating function. Let's let g of x be the sum and go from 0 to infinity of Cn x to the n. So we're writing down some function. The problem is this is useless if we don't have an explicit form for this. We need an explicit form. Right? So the question is, what is the best way to view this? And when you see a product like this, what do you think? Now, I could rewrite this. So I have my sum going not from 1 to n, but let's say L goes from 0 to n minus 1, CL, and then what would the other thing be? So it would be, you're saying it would be n minus L plus 1, so n plus 1 minus L? Or is it n minus 1? Right, so there's parentheses. So let's think. When we put in k equals 1, we have a n minus 1. And so when I put in L equals 0, we have an n minus 1. When I put in n, I get 0. When I put in n minus 1, I get 0. Good. So that's the way I should look at it. So what this is looking like is this is a multiplication of things. So let's imagine I have two different functions. And again, we're not going to worry about convergence or anything like that. Let's say I have f of x is the sum of an x to the n, and g of x is the sum of bm x to the m. I could look at f of x times g of x. And that's going to be a sum of, Cn, well, let's do ck, x to the k. How would I figure out what the ck's are?
It would be some sort of combinatorics thing, because you'd say, or maybe not combinatorics, would be the coefficients.
Yeah.
But you'd say, a1 plus dk minus 1.
So I don't think it's going to be pluses.
dk minus 1 plus a2 times.
Yeah. So if I wanted to get c0, this is the coefficient of x to the 0. I would have to have a0 times b0. Right? If I want to get c1, I have to have an x term. I could have an x term here and a constant term here. So I could have a1, b0. Or I could have the constant term here and the linear term here, a0, b1. If I wanted c2, I could have the quadratic term here. I could have, a2, b0 plus a1, b1 plus a0, b2. And the question is, do I want to start off with the index here large or small? Given that I'm writing it small than large, I probably want to do it the other way. It doesn't really matter, but let's, we haven't written too much yet, so we can fix this without too much trouble. a0, b1 plus a1, b0. a0, b2 plus a1, b1 plus a2, b0. And in general, ck would be a0, bk plus a1, bk minus 1, all the way down to ak, b0. So these are relations for the c's in terms of the a's and the b's. The question is, when would this converge? Well, if the a's and the b's aren't growing too rapidly, if I choose x to be sufficiently small, this will hopefully converge. This is where you try to remember some results from Calc 3 or real analysis, where you've hopefully talked about series convergence. Or you just argue formally. And then later we can see that for all the stuff we're doing, things aren't growing too rapidly. So for the Catalan numbers, we have 2n, choose n. This is clearly less than or equal to 2 to the 2n over n plus 1. Because this is a binomial coefficient from x plus y to the 2n. Clearly can't be worse than just 1 plus 1 to the 2n. And in fact, this is less than or equal to 2 to the 2n. So we know these coefficients are going at worst, if you want, 4 to the n. So if I take my x to be less than maybe 1/4 to the n, I might be okay. Maybe if I take them to be like 1/5 to the n, I will have so much decay, I should be fine. So these quick dinky estimates are often enough. So even though we didn't know this, we did know this was true. We knew Cn was definitely less than 2n choose n. So while it might have seemed like that was a ridiculous thing to be doing on Monday's class, it pays dividends here. It's enough to give us that the series will converge if x is less than 1/5. Okay, so the question is, does this help us? So we have these relations. What should we choose for A? What should we choose for B? Yeah.
How would we get out the, so like, if we wanted ck to be the same as like the index for L equals n minus 1,
Right.
then we would make k n minus 1, and we would make,
Okay, so if we want,
but then we would have terms beyond the ck. Like, how could you get the ck term, but also have there be no further term?
right, so unfortunately here things are a little bit, the indexes are a little shifted annoyingly, right? And this is one of the most annoying parts of the subject, is that we do not always have things phrased exactly as we want, and we sometimes have to tweak things a little bit. So we do have a recurrence relation for the Catalan numbers, right? So for Catalan, we know something. We know, we've just shown that Cn is the sum of Cl, Cn minus 1 minus L. L goes from 0 to n minus 1. What would you have loved to have there rather than Cn? What index would you have liked to have had here? Cn minus 1. Or what would you have loved to have had here? Yeah, life's hard. Deal with it. Sorry. So we don't have exactly what we want. But it's shifted by just 1. How do you shift by 1 in a power series? What do you multiply by? X, or 1 over x, depending on which way you want to shift. So it's not really that big of a deal. So what this is suggesting is, what should we take for our a's? What should we take for our b's? This should be al, this should be b, n minus 1 minus l. And what we should do is, it's called self-convolution. Let's multiply the function by itself. So let's define f of x to be the sum of C L x to the L. And then if we look at f of x times f of x, that's going to be the sum. And then what we'll have here is we'll have C L and then C m minus L x to the m. L goes from 0 to infinity. Everybody comfortable with this? So here, if I want just the mth coefficient, I would replace k with m. What I really want is I want the n minus first coefficient. So if I take m to be n minus 1, so I actually have a double sum here. So first, I have the sum L goes from 0 to m. That gets me this coefficient. And then I have a sum m goes from 0 to infinity. OK, so we're almost there. We just have to figure out how to clean things up. So probably shouldn't have erased that, but so we've got f of x squared is the sum m goes from 0 to infinity, and then the sum L goes from 0 to m of CL C m minus L x to the m. What is this coefficient equal to? Cm plus 1, right? So our recurrence is that Cn was the sum of, we did CL, Cn minus 1 minus L. L goes from 0 to n minus 1. So if we want n minus 1 to be m, then that means m is equal to n minus 1, or n is equal to m plus 1. So we then just get Cm plus 1 is the sum L goes from 0 to m of CL Cm minus L. So it's just playing games with the indices. And so now that we know that, we can use this to substitute for this. And we'll get f of x squared is the sum m goes from 0 to infinity of Cm plus 1 x to the m. What would you like to change? Multiply by x. So we have to then divide by x. So this would become 1 over x, the sum m goes from 0 to infinity of Cm plus 1 x to the m plus 1. What does that almost look like? F of x. It's not quite f of x. Why is it not f of x? It doesn't have the constant term. So what's so nice about this proof is we're doing the two most powerful techniques we have in mathematics. We just multiplied by 1, and now we're going to subtract 0. So we add in the constant term and then subtract it, and then we can replace this with f of x. And so we end up getting f of x squared, let me see this, is going to be 1 over x, f of x minus c0. We have a formula for f of x. We have an explicit formula, right? So I'll do a little bit more analysis with it. So we've just shown that f of x squared is equal to 1 over x, f of x minus c0. And what does c0 equal? How many paths are there starting at the corner, ending at the corner? 1. So we can just put a 1 there. So we get x, f of x squared, minus f of x plus 1 equals 0. What do we do? How do we do this? Quadratic formula. So this may be the first time in your lives you've used the quadratic formula for a function. So we can solve for the function. So f of x is equal to negative b, which is 1, right? Plus or minus the square root of b squared minus 4ac, which would be 4x, I think, all over 2x. And good. And you're seeing beautifully. Excellent. Make sure you email me with this. Clear. In fact, everybody who's making comments, please email me. I need these for letters of recommendation. I occasionally have people who contact me after 8 years. And it's nice to be able to look back in records. And so please email me. So clear, you need x less than 1/4. Well, less than or equal to 1/4. At 1/4, things could be okay. But if x was greater than 1/4, you would have an imaginary number here. The number of paths is not going to be imaginary. So you're immediately getting the series expansion is going to break down where you expected it to. Wonderful. Now, there's a little problem here. What's the problem? So when we look at this, something looks a little bit fishy. Yeah, we have 2 functions. The number of paths should not be multiple valued, right? The number of paths, that's a number. There's not 2 different answers for how many paths there are. What went wrong? What do we need to do?
I think with the quadratic formula, when you solve for it, at some point you take the square root of something so fast as a negative.
Ah, so one of the square roots probably doesn't belong.
So you need to look back at
Excellent.
the derivation of the quadratic formula and figure out where you can.
Well, they're both fine. They're both roots to this problem. But whenever you square things, you always run the risk of introducing phantom roots. So one of these roots will not be physically realistic. Now, if you look at our series, we know the Catalan numbers are at most 4 to the n. And so we believe that as long as x is less than 1/4, the series should converge. Imagine I'm a nice professor. It may be difficult to imagine this, but try to imagine I'm feeling generous and I decide to give you an easy problem. A real marshmallow. I want you to evaluate f of x exactly. Now, I know you don't know the Catalan numbers yet, but I want you to evaluate f of x exactly, and your entire grade for the semester depends on this. But I will let you choose any value of x. Really? You choose 1/4?
If you choose 1/4, then the square root disappears.
But we have a plus and a minus.
Right, but it's 1 plus or minus 0.
You may be just okay. But that's okay. So you will be safe if you choose 1/4, but you will not know which is correct, the plus or the minus. But so you're correct. The way I phrased the problem, I've got to be more careful. You survived the challenge, your grade is safe, but you don't know which is the plus or the minus. I claim there's one special point you can evaluate it at, and then figure out is it plus or minus. 0. When in doubt, you always want to be trying points like 0 or 1 because that's really nice for x's. So what must be the case? Is this well defined when x equals 0? Oh, okay, we're getting some smiles now. So f of 0 is just c0, which is 1. So this is going to tell us which root works. At x equals 0, this has to be well defined. So notice that if I take x equals 0, I've got 1 plus or minus 1. If it's 1 plus 1 over 0, it blows up. So it's got to be 1 minus. So the solution is f of x equals 1 minus the square root of 1 minus 4x over 2x, as otherwise blows up. So now we know the generating function. It's the same miracle as the Fibonacci's. Except in this case, I think the miracle is a little bit stronger, because for the Fibonacci's, I can give you a divine inspiration. I can give you the divine inspiration for the Catalan numbers, but you need a lot more commentary for the divine inspiration to actually see that it works out. Whereas here, we now have the closed form expression. Now the only problem is we now have to expand the square root of 1 minus 4x. So I will say just a few brief words about that and then leave that as an exercise. So we've almost solved the problem. So we know that the formula is 1 minus the square root of 1 minus 4x divided by 2x. So we must expand 1 minus 4x to the 1/2. Anybody know how to do this?
It's just the same as a binomial theorem, except because on factoring.
Yeah, it's a little bit more involved. So Newton has a formula for the expansion of this. If the exponent is not an integer, it's much harder. But how do we do this? We just do this by Taylor series. Right? This will equal, let's call this function g of x. This will be g of 0 plus g prime of 0 times x plus g double prime of 0 x squared plus g triple prime of 0 x cubed. And what mistake did I make? Yeah, I forgot to put in the factorial. It's 2 factorial, 3 factorial. When we do our Taylor series like this, we want this way so that if we take 2 derivatives, the 2 comes down as a 2 factorial, cancels this. These 2 are killed because they're only up to x. When I put in x equals 0 and I take 2 derivatives, all these will be killed, and I'll get the second derivative is g double prime of 0, which is what the second derivative should be. If I were to take 3 derivatives and evaluate at 0, these would be killed because they're at most x squared. Everything beyond here would be killed because it's x to the 4th. And then the 3 would come down as a 3 factorial. So all we have to do now is calculate the derivatives of this and hope that there's a nice formula. You should have a strong idea of what that nice formula is, right? And then we have to be a little bit careful because to get our Catalan numbers are defined as, cm x to the m. We have the factorials here. We're going to have to play games. But there's a binomial coefficient that we think is the answer, right? So given that there's a binomial coefficient and there's factorials in the bottom, that could actually be good. We also have a 4x. That's a little bit problematic, but we also have this 1/2 as the exponent. So maybe the 1/2 and the 4 are going to interact nicely. So I'm going to just start the calculation just so you can see it. So let's say g of x is 1 minus 4x to the 1/2. So g of 0 is just 1, which is really good because we're going to have 1 minus that over 2x. We better not have a constant term because we are dividing by x. So the first term that will survive will be the linear term, which when we divide by x will be fine. All right, so now let's calculate g prime of x. So g prime of x is going to be 1/2, 1 minus 4x to the negative 1/2. And now the derivative of negative 4x will be negative 4. So it will become negative 2, 1 minus 4x to the negative 1/2. And what's nice is whenever we put in x equals 0, this part will just vanish and we'll just get this coefficient. So we'll get g prime of 0 is just negative 2. G double prime of 0, I'm sorry, g double prime of x will be, now we take another derivative of this. Now what's interesting is at this point we have a negative 2, we have a negative from this, and we have a negative from this. So negative, negative, negative is always going to be a negative. So we'll have negative 2 times 1/2. I'm going to drop the negative sign. Well, I'll leave the negative sign. Then we'll have a 1 minus 4x to the negative 3/2, and then we'll have a negative 4. Okay? The negatives, so we get g triple prime of x is, these cancel. I think it's now negative 4, 1 minus 4x to the negative 3/2.
I think you meant by double prime.
Double prime, yes, thank you. Now what's interesting is we're going to pull down a 3. Then after we pull down a 3, the next time we're going to pull down a 5, then a 7, then a 9. What are these looking like? You will have 3 times 5 times 7. 3 times 5 times 7 times 9. What does it look like? It looks like a factorial, but it's not a complete factorial. So what I want to do at this point is I'm just going to give you some clues, and I'll let you either finish it on your own or read online as to how you would finish this. So let's say you have 9 times 7 times 5 times 3 times 1. Okay? This looks a lot like a factorial. How many of you have ever seen this before? This actually has a special name. This is 9 double factorial. Double factorial does not mean the factorial of the factorial. You could have defined it that way. It just turns out that every other is a far more useful quantity. What would you have loved to have had here? Yeah, so let's just put them in. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Are you allowed to just throw terms in the numerator? You must divide. So we'll divide by 8 times 6 times 4 times 2. The top is just, and in fact, it's a little convenient, I think, here to put in the 10 as well. The top is just 10 factorial. What's the bottom? It's another double factorial. It's every other. Excellent. Make sure you email me. It's 2 to the 5th times 5 factorial. We can pull out a 2 from everything. Notice how we keep getting 2's from this. Things are going to balance out miraculously when you do this to get the Catalan numbers. And what I hope you can begin to see is where this 2n choose n is going to come from. Is we're going to be getting half of a factorial from here. We'll complete it. We'll put it down. We already had half of factorial down below. I was too excited. I walked too quickly and the camera didn't follow me. We have factorials coming in down below from this stuff over here. When we take the odd stuff and put in the other stuff, it's going to balance out over there. We're going to have all these 2's that we need, but we have these 2's coming from the 4's, so they'll cancel, and everything is going to work out. And you will get 1 over n plus 1, 2n choose n when you finish this. Okay? So we need to use Newton's binomial theorem. We need to use generating functions. There's a lot of really good problem-solving techniques in this. So if you've never seen generating functions, this is why I really wanted to cover that in this class. It is phenomenal how this works. Is you start off, we don't know what the CN's on. We build a function. But we do know the CN's. We just don't know that we know. We know everything about the CN's because we have the recurrence relation. It's how can we get something useful from it. We create this global object. And that's the whole idea. We create a global object, and then that gives us local information. So it's a lot of work to get that local information. Okay. Did anybody look at the extra credit problem on finishing up the cookie problem or Waring's problem for the first one? Okay, were you able to get it?
I mean, I solved it in a similar way to just how I solved it originally, except instead of cookies, it was x to the whatever. It was just like kind of, as I recall, it was like n different summations.
Okay. So, I mean, what we had for the cookie or Waring degree 1, we want to solve x1 plus, xp equals c, the cookie problem. And we saw we could look at 1 over 1 minus x to the p, and this is going to be the same as the sum x1 equals 0 to infinity, x1 to the n1 of the bed. I think to keep using x as the variable, because that's different than these. So let's do we'll do n1 to np. Dot, 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 sum xp equals 0 to infinity, xp np. And when I collect terms, it's got to be of the form something x to the n. And what it's going to be is it'll be the number of ways of writing n as a sum of exactly p factors.
Yeah, and then, I mean, the way that I did the cookie problem was, I thought of it as, like, how many ways can you give, can you split C rings among n fingers?
Right.
And then,
so you're doing this with a partition?
yeah,
Right.
line it all up.
Right. So that's the clever way to do it. But that way is going to break down when you try to do higher problems. So my question is, once we have this, we actually have a global object. How do you pick off the nth coefficient of this?
Why couldn't you use partitions?
You could, but what I'm trying to say is we're studying generating functions. And the whole idea is if you have a generating function, if you have the coefficients you want in terms of a nice explicit function, you need to figure out how to do the series expansion.
Isn't that the p derivative of 1 over 1 minus x
Yes.
divided by p factorial?
Exactly. So can you calculate the pth derivative of this? It's not going to be that bad. Because what's nice is, unlike other problem where we had the square root, if we take the p, we'll have p 1 minus x to the p minus 1. So let's just quickly look at what the derivatives of that are going to be. So again, these generating functions are only useful if you can do something with the global object. So we need derivatives of 1 minus x to the negative p. And let's call that h of x. I don't think we've used h for a while today. So h prime of x would be negative p, but we're going to have a negative coming from this, so it'll just be p. 1 minus x to the negative p plus 1. And then h double prime of x would be p plus 1, 1 minus x to the negative p plus 2. And you can again see that this is looking a lot like a factorial. But it's missing some terms. So you'd multiply by p minus 1 factorial over p minus 1 factorial. You've got another factorial coming from the Taylor coefficients. And you can begin to see where the binomial coefficient is going to come from. So it's a nice exercise. I strongly urge you to finish the calculation and see how you can get the binomial coefficients coming from this. One last thing which I should have remarked a moment ago is what you'll see here is the coefficients are going to be positive. In what we had a moment ago, all of our coefficients were negative. Well, that was good, because we had 1 minus the square root of 1 minus 4x. If all the coefficients here are negative, when we multiply by -1, they'll all become positive, so the c's will all become positive numbers, which is good. You should not have a negative number of ways of doing something. So you always want to do these sanity checks. Okay, so this allows us to avoid being clever. This allows us to avoid having to figure out partitions. That's, I think, the best way of doing this problem is with partitions, but there will be other problems where that won't work or where it's not clear how to look at it. And so if you can have a machinery that you can just crank through, that's phenomenal. And that is why I love generating functions so much. The difficulty is extracting things. Here it's not too bad to extract. You know, we take the derivatives aren't that bad. And then we have to do a little bit of combinatorial, a little bit of algebraic manipulations to get it nice. Not a horrible amount, but a little bit. Okay, everybody comfortable on this? So we've got about 15 minutes left. I thought I would use the last 15 minutes to describe the most beautiful idea I have seen in mathematics. When I was a young postdoc at Ohio State, a professor asked me what I thought was the most beautiful idea. And I said the circle method, and he said, "You're young." It's been almost 15 years. I have not changed my mind. I would still say the circle method is the most beautiful idea I have seen in all of mathematics. And I've been around a bit. It is phenomenal. It allows you to attack problems that mathematicians initially said should not be attacked. So who's familiar with Goldbach's problem? Anybody know Goldbach's famous problem? So there's two versions. There's the binary and there's the ternary. The binary is all large evens are the sum of 2 primes. It's open, and we believe large is greater than or equal to 4. I'm sorry, large means 4. That once you get up to 4, that's how high you have to go. The ternary is all odds, all large odds are the sum of 3 primes. And it's a theorem, actually. We've finally proven it a few years ago. And here, large equals 7. You can't write 5 as a sum of 3 primes. You can't write 3. You can't write 1. But 7 you can write as the sum of 3 primes. So from 7 onward, we now know it's true. The initial proofs show that all sufficiently large odd numbers are the sum of 3 primes. And then, unfortunately, the sufficiently large was like 10 to the really large number, way out of reach. And finally, we were able to winnow it down low enough so that the computers could just check by brute force up to a certain height. So these were described initially as problems that mathematics should not be concerned with. And the reason is, when you think of primes, what property do you think of? So when I give you a couple of primes, what do you want to do with them? You want to multiply them. Why would you add them? Right? Primes are not meant to be added. They're the multiplicative basis of our number system. Why are we multiplying them? These questions don't make sense. Now, you can ask them, but some mathematicians say you should just not be considering stuff like this. This is not in the realm of what mathematics should be looking at. We could look at it more generally, however. Imagine you have a couple of sets. You could look at what is A1, plus, maybe what's A plus B plus C, where you choose some element from set A, some element from set B, and some element from set C. And you ask, what can you get? You can actually phrase Fermat's last theorem in this way. Let's let Pn be the set of nth powers of positive integers. So this would be 1, 2 to the n, 3 to the n, 4 to the n, etc. Pn, plus Pn intersect Pn is empty if n is greater than or equal to 3. That's Fermat's last theorem. You can talk about differences between primes. That would be the set of primes minus the set of primes. What can you say about the values it attains? There's a whole slew of problems that can be attacked by generating functions. And so what I want to just show you very quickly, in 10 minutes, I don't want to go through all the details. If you really want to, either let me know or take a class I'll teach next year. I want to show you how we can attack problems like this. The original method, the original formulation of the circle method was more in terms of power series and complex analysis and infinite sums. What's the danger with an infinite sum? Yeah, it could blow up. And so whenever you have an infinity, you have to be careful. The new version of the circle method we have now uses finite sums and uses trigonometric functions instead. It also no longer has a circle. It's still called the circle method. So in complex analysis, we used to do things along a circle. Now we do things along the wrapped unit interval 0, 1. And so this is one of the greatest problem-solving techniques I know. So the idea is the following. How many of you have not seen this function e to the ix? Okay. So this is cosine x plus I sine x. One way you can see this is you can do Taylor series expansions. We know e to the u is the sum of u to the n over n factorial. Cosine of u is the sum of u, negative u squared to the n over 2n factorial. Similarly for sines, I squared is negative 1. And when you do all of this stuff, you will end up getting the formula for e to the ix. It turns out that there's a lot of work to prove something like this. But if you had these Taylor series expansions, you can see that e to the ix is cosine x plus I sine x. And what's so useful about this is we can form a nice class of functions. So Taylor series are expanding things out in terms of 1x, x squared, x cubed. We're going to use trigonometric series. And so, e to the 2 pi I nx is cosine nx plus I sine nx. So if you don't like the exponentials, just pretend I'm writing cosines and sines on every single line. And then just pretend that this is a convenient formulation. If I take e to the 2 pi I nx and e to the negative 2 pi I mx, and I integrate this from 0 to 1, this is the integral from 0 to 1 of e to the 2 pi I n minus m x dx. So this would be cosine n minus mx plus I sine n minus mx. If you integrate cosine and sine over a full cycle, what do you get? 0. So there's only one way when this integral is not 0. When is this integral not 0? If n equals m. If n equals m, you get cosine of 0x plus I sine 0x. Okay, sine of 0x is identically 0. Cosine 0 of x is identically 1. So this integral is equal to 1 if n equals m, and 0 if n does not equal m. It's a way of detecting if these two things are the same. And again, if you don't like working with the exponentials, you can work with cosines and sines, multiply, do all those trig identities. If people want, I'm happy to give a lecture on proving trig identities. These are not bad things to know for problem-solving competitions. And you can prove every trig identity from these. Do people want to see trig identity proofs?
What do you mean,
Like cosine x plus y, how it follows from these relations. Okay, so I will, if you change your mind, let me know. So the whole point is this detects things. So again, this is just the real 5-minute introductory spiel to the circle method, that we have a way of attacking these problems. And this idea of generating functions, this is not just a toy to handle things like this. Let's let fn of x be the sum over all primes less than or equal to n of e to the 2 pi I px. P is a prime. Just so I can sleep at night, I really should put a log p weight here, because you learn if you go further in analytic number theory that you should not count primes equally. You should discriminate, but only small amounts. And you weight larger primes a little bit more than smaller primes. It just makes the formulas nicer. We're not going to deal with that. We're not going to put in the log p weights. But if you actually wanted to do the method, it would make things easier. Let's look at fn of x cubed. This is going to be the sum of p2, p3 less than or equal to n of e to the 2 pi I p1 plus p2 plus p3 of x. Right? So if I just cube this, I'll use a different dummy variable every single time, and I group all the terms. So this is the same as the sum over n less than or equal to 3n, and I'll call it a 3n of n e to the 2 pi I n x. This is the number of ways that you can write n as the sum of 3 primes, where each prime is at most n. If I choose big N to be larger than little n, it's the same way as the number of ways of writing little n as the sum of 3 primes. I can't use a prime bigger than it. So here is my answer. The coefficient tells me. All I have to do is figure out what that coefficient is. Well, we haven't erased it yet. Thank God, right? We have a way to calculate those coefficients. So what we do is we take fn of x cubed, we multiply by e to the negative 2 pi I mx. We integrate this from 0 to 1, and this will just be a 3n of m. So if you want to know, is your number representable as the sum of 3 primes, just do this integral. If you thought your teachers gave you any integrals that were hard in Calc 1, Calc 2, or Calc 3, they have nothing on this. This integral involves a sum over primes. The primes are being exponentiated in cosines and sines. This is an absolutely nightmarish integral to do. Just because I can write something down does not necessarily mean I've made progress. Here's the answer. Now the good thing is I actually don't have to evaluate it exactly. I just have to show it's not 0. Right? What can you tell me about this integral? So describe this integral. What kind of properties does it have? What must be true about this integral? What word would you use to describe this integral? So imagine it's a police lineup. You have a bunch of numbers, and you know some number hurt you, and you want to describe the number that hurt you. How would you? What kind of property must this number have? What does this number represent? It represents the number of ways of writing m as the sum of 3 primes. Each prime is at most big N. What can you tell me about this number? What kind of property must it have? What must it have? It must be an integer, right? So I just have to show that it's non-zero. Better yet, I just have to show it's greater than a half. Because if it's greater than a half and it's an integer, it's got to be at least 1. There must be a representation. So the way that it works, and this is kind of ridiculous, the way we show an odd number m can be written as a sum of primes is we show it can be written as a sum of primes many ways. Therefore, it must be representable as a sum of a prime at least one way. This is one of our most powerful techniques. We show something happens many times, so it happens at least once. If you think back to the triangle game we were playing with Kayla, there's always going to be a triangle with 3 distinct vertices. And the way you show that is you show it happens an odd number of times. What's the smallest positive odd number? 1. Therefore, there must be at least one such triangle. This is one of our most powerful proof techniques, and we'll talk about this. We'll analyze the triangle game later. All right, so this is a good place to stop.